Okay, so I'm going to just do some quick Riemann-Roch warm-ups. Uh, so, um, so RD and ID, I can only change by one. Okay, so that means if I add a point to this or subtract a point, the values of these will only change by one. Phi d is injective, so this map associated to a divisor, if and only if for all points in the curve. So again, here we're working over curves over algebraically closed fields. So for all points in C, we have h0 of d is equal to h0 of d minus p plus 1. Okay, so when we subtract a point, we actually decrease. Okay, the other thing that phi d is an embedding, if and only if for every 2 points. Okay, they may be the same point. P might be equal to Q. H0 of D is equal to H0 of D minus P minus Q plus 2. So we decrease by 2. Okay, so this separates points, and this separates tangent vectors. So when we're going to shrink these together, we'll see that this tangent condition comes up. You might recall that an embedding is an injective immersion. So since we're working over C, this is so an immersion means you're injective on the tangent spaces, and then injective means injective set theoretic map. Okay, so there exists something in the function field. Okay, so if there exists a guy in the function field with divisor just like subtraction like this, then the curve is isomorphic to P1. So that's that. Okay, so so then we have some statements about GRDs. The only G minus 1, G minus 2 is the canonical one. So it's the canonical divisor. So remember that a GRD is a linear series, right, where the embedding is embedded as degree the d, and then it's in a projective space of dimension r. Okay, so C is hyperelliptic if and only if there exists G12. So this is going to be the hyperelliptic map. Here again, the R is equal to 1, so it's a map to projective space, and the 2 means it's embedded as degree 2, or it's a degree 2 map. Okay, and then okay, so if C is non-hyperelliptic, G is bigger than or equal to 3, which implies that, and G is bigger than or equal to 3, this implies that the canonical embedding, canonical map is an embedding. Okay, so proofs. Okay, so the idea is that RD minus, so for the first thing, ID is equal to G minus, or D minus G. So D is the degree of the divisor, G is this, and then D plus P minus I of D plus P. So this is equal to D minus G plus 1. So D plus 1. Okay, and so this tells us that RD plus P minus RD plus ID plus P, let's say ID, plus ID minus ID plus P here is equal to 1. Okay, and these are both positive quantities. This is positive. To see that these are positive, you should notice that this is related to H0. So we have O of D plus P. Okay, contains O of X of D, and then here, okay, this is for this, and then you need to do the same thing using that this is H1, and then relate it by Serre duality and do the same thing. Okay, so they're both positive, and so two positive quantities adding to one gives you the result, gives you what you want. Let me put this here. Okay, so injectivity. So what do we want to say about injectivity? So what we need to show is that for so let's say phi is equal to let's say f0 of x, f r of x. Okay. So we have this map here. These guys are these global sections of CD. Okay, so they're really functions with poles at worst d along this divisor. Okay, so we need to show that. So let's say p is not equal to q. Then it's injective. Okay. Meaning that when p is not equal to q, we'll have this and that f0 of p up to fr of p is not equal to f0 of q up to fr of q. Okay, and what does this mean? So since these are not equal, there exists some relation satisfied by one and not the other. So in particular, there exists some a of so f0. So we'll take some linear combination of these guys. Okay, and this is going to be called the f, such that f of p is equal to 0, let's say, and f of q is not equal to 0. Okay, since this is true, this f this is true if and only if this equivalence class of f in h0 of d minus h0 of d minus q has dimension. So this is this and this is not 0. So the dimension is bigger than 1. Okay, and it has dimension less than or equal to 1 by the previous remark. So this says that it is dimension exactly equal to 1. Okay, so this is saying, okay, so again, why is it not vanishing here? So f of q is not equal to 0. So this condition here prescribes vanishing at q, and here we have that this is not equal to 0. So it's not going to be equal to 0 in this quotient. Okay, so that shows that it is dimension 1. And then you can go if and only ifs the whole way. Okay, so to do the embedding, so take P and Q to be in C. Okay, and we're going to look at H0 of D quotiented by H0 of D minus P minus Q. So this is contained in here. There's some extra vanishing conditions. And this, now we're going to write down the flag, right? So we're going to write H0 of D, H0 of D minus P, quotiented with H0 of D minus P of H0 of D minus P minus Q. So each have dimension 1. So there's some, there's a school outside and there's children screaming. Okay, so there's this. Okay, so each has dimension 1. Um, uh, Oh, okay. So each of these has okay. So if this is dimension 2, so okay. So if this has dimension 2, each of these have at most 1, so they each both have to be dimension 1. Conversely, suppose. Okay, so what am I doing? I'm doing. Sorry, I was distracted for a second. So I'm doing this one here. Okay. So first of all we need to show that it's injective. Okay, so let's suppose this, and then I'll show it's an injective. Okay, so if it's injective, so first of all, sorry. So which way do we want to assume? Let's assume that this is true. Okay, if this is true, then this side will have it at least dimension. This side will have dimension 2, and each will have dimension 1. Okay, so this implies that this has dimension 1, which implies that it's injective. Okay, so that's what we have. So we showed that this shows injective. Now we need to show that it's an immersion as well. So conversely, suppose that it's an injective immersion. Then if it's an injective immersion, then what we're going to have is that this has dimension 1. Okay, and then so that takes care of injectivity. So injectivity follows from the previous part and the discussion that I just said. Okay, so now we need to talk about the immersion property. So this is so what we'll do is we'll take P and Q and we'll have them get closer and closer together. So let's do that. So we'll look at the immersion property. Okay, so we know that so we have H0 of D of H0 of D minus P. So we take P is equal to Q. Okay, and we'll do this flag or thing. So we'll do D minus P and H0 of D minus 2P. Okay, so here so we're going to find there's an F here which is not 0. Okay. So both of these are one-dimensional, so this guy is here. So what this says is that f of p is equal to 0, right? But like its derivative is not. So what we need to do is we work locally. So let t be a parameter. At p, so we take a local parameter at p, and so then we can write f as 0 plus a1t plus a2t squared plus whatever, so that we can expand it in a power series. Okay, so and what this says, so the fact that it's in here and that it's not 0 says it vanishes once but not twice. So this condition says it vanishes once but not twice. Okay, so this is what we have. And so F was, again, so F is in D in here, and let's write down some generators for this. Okay, so phi, as we wrote before, was like this, F0 to FR, and these are the global sections here. Okay, and so what we can write is in some coordinates. So after choosing coordinates, so let's say we use this local parameter t. So this thing looks like df1 dt, or df1 dt, df2 dt, etc. dfr dt. Okay, and we know that this is not equal to. So this has full rank. rank by existence of this f. So f is going to be some combination of these fi's here, and the derivative is linear, right? And then we know that when we plug it so it's full rank at p. Okay, by the existence of f. Okay, so then there's some linear combination of these things which is not going to be 0. Okay, so that shows that if we have this property about there being this thing having dimension 1, so this one's dimension 1 and this one's dimension 1, then we get this non-zero derivative which shows that it's an immersion at p. Okay, so okay, and then conversely, if you have an immersion at p, so that means that you can find some non-zero combination and it'll give you an element here. Okay, and that proves the other fact that we wanted to show. So that proves we're down here. So we had this here. Okay, now we want to show this one. Okay, so let's so suppose div f is equal to p minus q. So we have some simple thing here. Okay, so we apply the lemma. Okay, so we'll look at d to be just the divisor q. Okay, sorry, we'll look at d to be, let's see, yeah, just the divisor q. Okay, and so f will be an element of h0 of d, so it has poles at worst d, or worst q. Okay, so f is going to be an element here, and note that h0 of d, so the constant function is in here, right, and f is in here, so this is going to be two-dimensional, right, and then we have that h0 of d minus, let's say, 2 points, p1 minus p2. Okay, so this is just going to be a single thing. So this has negative degree. This is going to be 0. Okay, so this has to drop by 2. It can only drop by 2. So I guess we can say this is greater than or equal to 2, but it's going to be actually equal to 2 since it can only drop by 2. Okay, at most, and it will drop by 2. Okay, so this, by the previous lemma, shows that phi of d is an embedding. Okay, and so we have the global sections here. So this is spanned by 1 and f, and so we can write phi of d of a point to be equal to, let's say, a point p prime. So it's not different from this. So it's different from this to be equal to. So let's say f of p and then 1. Okay, so we're taking this f, and so this defines a map. Okay, so this thing gives a map from the curve to p1, which is an embedding. Okay, let's say, so like this is an embedding into p1. This is actually like you can actually check that this is a degree 1 map, a degree 1 morphism to p1. Okay, one way to see this, another way to see this is to look at like the inverse image of like phi inverse of, and then I'm going to write this like maybe affine, so that these are not projective coordinates. But this is you can actually look at that this is 1, so you can kind of check this. Okay, so we have a degree 1 morphism to p1. So this is an isomorphism. Okay. Okay, so where are we now? So here we just did this. Okay, so these two, let's omit these. But it's a fact that that if the only GRD, which has G minus 1 and G2 minus 2, is the canonical one, and that this is hyperelliptic, then this is here. I guess I can omit this. Well, Okay, so let me just do this one real quick. So if C is not hyperelliptic, then it's an embedding. Okay, so suppose G is bigger than 2, and phi kc is not an embedding. Okay, let's say that this is due to not being a map and that there's some base point. Okay, so there's something that you can't move. You can't move your linear series, or can't you move in your linear series to get away with this point. Anything linear equivalent to k has this point k. Okay, well, this would say that that the dimension doesn't change when we subtract this, so it's already automatically satisfied, and this is G. Okay, and so this implies that there'll exist a function vanishing at P and nowhere else. Okay, and which implies that C is isomorphic to P1 by our lemma. So we had our other fact that we proved that this fact here. Okay. Okay. That being said, so this gives us a contradiction because we assumed that the genus was bigger than 2. So this is nonsense. And we can say that this is empty. Sorry, this is equal to the empty set, and that H0 of Ck minus P is actually decreases this. So this is G minus 1. Okay, so by that C being non-hyperelliptic, the collection of G12s is empty. Okay, so this is a degree 2 divisor, right? So this tells us that for all Q, we have that H0 of C P plus Q is equal to 1. Sorry, is equal to is equal to 1. Okay, and this 1 here is due to the constant function. Okay, so we really only get the constant function. So R is going to be 0. Okay, so we're not going to get anything cool. Okay, so now we just do a little Riemann-Roch computation. C P plus Q minus H0 of C. Now we do minus P minus Q. So this is the canonical. Maybe I should probably put these everywhere if I'm going to do them. Okay, so there we go. And then this becomes equal to, so the degree is 2, and then we just use the Riemann-Roch formula, 1 minus G. Okay, and this side here, so from what we said, this is 1 minus H0 of Kc minus P minus Q. Okay, and then putting these together, we see that H0 of Kc minus P minus, okay, I'm switching notations. Whatever, I should put a C there since I've been putting it, but it doesn't really matter. This is going to be equal to G minus 2. Okay, so so we took arbitrary 2 points, right? And then so this is for all P, since the base locus is empty. So and then we said for any 2 points, this decreases by 2, and so this shows that that phi of Kc is an embedding. Okay, and that's what we did here. Okay, and that proves this one. All right, thanks for watching.